Hi, this is Swaraj Renge, roll number 20171119, and I'm going to talk about the Science 2 assignment 2. So the first question is to plot the mean number of particles versus epsilon minus mu for all of Maxwell-Boltzmann, Fermi-Dirac and Bose-Einstein statistics at low, intermediate, high and at t is equal to 0 Kelvin, and to plot these and to compare the results. So let's start with Boltzmann statistics. The equation for that is y is equal to e power minus x by kt, and at t is equal to 0 Kelvin, the graph becomes vertical because all the particles have zero speed due to the because there is no energy in the particles at 0 Kelvin. At a low temperature, most particles have low energy and lesser speed, so the graph is still vertical but drops off sharply towards higher values of epsilon. Then at medium temperatures, we get a smooth exponential decay as it is expected from the expression for average number of particles in a given energy level. And finally, for a high temperature, the graph becomes almost a straight line as there is a uniform distribution of the number of particles across energy levels. For Bose-Einstein statistics, the equation is y is equal to 1 by e power x by kt minus 1. Again, at t is equal to 0, the graph has a value of n at 0 and 0 for all of the values. N is the number of particles. At low temperatures, the graph has a high value at t is equal to 0 and then drops off sharply as a higher proportion of particles are concentrated around low energy levels. At an intermediate t, the graph again has a smooth decay and it peaks at the value 0, and finally for a high t, the graph is almost flat once again. For Fermi-Dirac statistics, the equation is 1 by e power x by kt plus 1. Here again, at t is equal to 0, the graph has a value of n at 0, and for all other values, as we talked earlier, it decreases at 0 for all other values. At low temperatures, the graph has slightly higher values at t equal to 0 and then drops off sharply as a higher proportion of particles are concentrated on low energy levels. At an intermediate t, again the graph has a smooth decay but also peaks at 0. The difference here is that the new graph resembles a logistic graph, and this graph has a point of inflection. Finally, at high temperatures, the graph is almost flat, like for the same reasons that we talked about above. Based on this, we can make some observations that at t equal to 0, the graph has a value of n at 0 and 0 for all other values. At low temperatures, the graph has a high value at t equal to 0 and then drops off sharply. So we conclude that more particles are concentrated on smaller energy levels. At an intermediate t, the graph has a smooth decay and has the highest value at 0. The difference is with the Bose-Einstein statistics graph is that it resembles a logistic graph and it has a point of inflection. At high temperatures, the graph is flat almost once again. Moving on to the second question, we talk about the applications of Fermi-Dirac statistics. We've listed a bunch of applications. So the first one is to model metals as a gas of electrons. We can model metals as a cloud of negatively charged electrons in a positively charged background. Since electrons are fermions, this is a natural setting for us to use Fermi-Dirac statistics to get information about the system. One interesting observation is that using this method, as t approaches 0, the pressure exerted by the system tends to a constant non-zero value. This is as opposed to if we had followed the Maxwell-Boltzmann statistics, where pressure exerted approaches 0 along with temperature. Hence, the pressure exerted is a direct consequence of the fact that we use Fermi-Dirac statistics to model the system, whose fundamental difference is that the Pauli exclusion principle is followed. This non-zero pressure is called the Pauli pressure and is a consequence of the Pauli exclusion principle. The bulk modulus of a metal, that is the measure of how resistant a metal is to compression, is mostly a consequence of this Pauli pressure. Clearly, Fermi-Dirac statistics give a more accurate model than the Maxwell-Boltzmann statistics at low temperatures, especially for metals. The derived expression for specific heat, unlike the classical counterpart, also leads to a physical accepted value for the Lorentz number of metal. Then we talk about white dwarfs. One of the first applications of Fermi-Dirac statistics was in astrophysics, when Fowler applied it to study something called white dwarfs. He proposed that we may view white dwarfs as a gas of electrons and nuclei. The pressure generated by the fermions due to the Pauli exclusion principle, similar to the pressure in metals, will halt the gravitational collapse of a star if its mass is below a certain mass, and this limit is called the Chandrasekhar limit. If the mass of a star is below this threshold, then the collapse is stopped as the fermionic pressure is greater than the inward pull of gravity. But if the mass of the star exceeds this limit, then the star collapses to either form a black hole or a neutron star, as the inward gravitational pull exceeds the outward pressure. We can also use Fermi-Dirac statistics for modeling nuclear phenomena. Physicists have used Fermi-Dirac statistics to model nuclear phenomena such as the Thomas Fermi theory for the electron structure of many body systems. Other applications include the Fermi gas model to calculate the binding energy of the nucleons in the nucleus. Finally, we can use it for solid-state physics. Fermi-Dirac statistics has found a wide range of applications in the theory of semiconductors and metals. It was found that the behavior of holes in the semiconductors can be modeled as fermions, and as they obey the Fermi-Dirac statistics. It was also found that electrons which cause conduction, called conduction electrons, also obey the Fermi-Dirac statistics. This allows us to get to know about their theory in much more detail. Finally, problem 3 is what is the Bose-Einstein condensation, and a little more detail about that. So, a Bose-Einstein condensation is a state of matter that occurs when extremely low-density bosons are cooled to near zero temperatures. Since multiple bosons are allowed to occupy the same energy state, upon cooling, all the particles occupy the lowest quantum states. In such an ensemble, the microscopic quantum phenomena, such as the wave function, interference, etc., become apparent macroscopically. We can visualize this in this video. When the particles are cooled, they act like waves, and they slow down and the energy decreases. So these bosons are particles reduced to have the same energy at the same time. For example, photons. We can see at sufficiently low temperature, the waves of the bosons overlap, and all of them can be described by a single collective quantum wave. This exotic form of matter is called a Bose-Einstein condensate, and it was predicted by Albert Einstein and Satyendranath Bose nearly 100 years ago. And it took until 1995 to achieve the first Bose-Einstein condensate matter made of alkali atoms. So bosons are particles that are indistinguishable and are opposed to fermions in that the two bosons can occupy the same energy state. Now consider a system of two particles and two energy states. If they were classical particles, then there would be 4 possible configurations. But since the particles are bosons, they are indistinguishable, and there would only be 3 possible states. The state in which both are in different energy levels would become equivalent, as they are indistinguishable. Thus, the probability that they are the same state would be more than the probability that they are in different energy levels. Thus, we say in general that bosons tend to be in the same state. That is, they are more likely to be found in the same state. Now consider gas of molecules with some total energy. As the temperature is lowered, the energy of the system is lowered, and the desire for the particles to stay in the same state starts to dominate. Thus, at some point, it so happens that a large fraction of particles ends up in the smallest possible energy state. This is the Bose-Einstein condensate, where the condensed particles behave like a single quantum energy entity. So, how do we condense bosons? Bose-Einstein condensation was first observed in liquid helium in 1938. Liquid helium at temperatures of about 3 Kelvin condenses into a state called a superfluid, which demonstrates some interesting properties such as zero viscosity, etc. In modern times, the process to condensate a Bose-Einstein condensate is standard. The first stage of cooling achieved by is a set of laser beams propagating in different directions. The next stage of cooling is by evaporation by trapping it in specially designed magnetic fields. Now, to get Bose-Einstein condensates, the trapping magnetic fields are reduced so that the atoms expand freely, and this is how we condense bosons. Some applications of Bose-Einstein condensate are in dark matter research. Some of the models of dark matter interaction follow the Bose-Einstein condensation framework. P. Sikivi and Q. Yang had shown earlier that cold dark matter axions form a Bose-Einstein condensate by thermalization because of gravitational self-interactions. Some other applications are precise measurement detectors. These tools can be built that utilize the Bose-Einstein condensates and their experimental setups. In network theory, Bose-Einstein condensation in networks is a phase transition observed in complex networks. This phase transition predicts a winner-takes-all phenomena in complex networks and can be mathematically mapped to the mathematical model explaining Bose-Einstein condensation in physics. It can also be used for the development of optical lattices. Optical lattices with Bose-Einstein condensate could be used to develop highly sensitive instruments. For example, Bose-Einstein condensates trapped in an optical lattice could be useful for the next generation of atomic clocks, which exploit vibrations in the optical range. By comparison, the cesium standard used by many atomic clocks operates at microwave frequencies. Finally, we use it for quantum information processing. Quantum computers promise to perform certain types of operations much more quickly than conventional digital computers. But many challenges must be addressed before these ultra-fast machines become available. Among them, the loss of order in the systems is a problem known as quantum decoherence, which worsens as the number of bits in a quantum computer increases. Bose-Einstein condensates could be used to address this issue by building communication channels among smaller quantum computers for propagating the quantum state. This has been the explanation for science 2 assignment 2.